Good evening. On the 18th of June 2015, British astronaut Tim Peake safely returned home after spending at least 6 months on board the International Space Station. Tim has had a unique vantage point to see the Earth from space, so now seems a good time to mark the occasion by taking a look at our planet in more detail. We are fortunate that all of the conditions are just right to allow life to flourish here on Earth, and that the progress of evolution has allowed us humans to become the intelligent species among the huge diversity of life on our planet today. There is nothing unusual about the Earth's orbit. Our average distance from the Sun is about 93 million miles. The sidereal period is 365¼ days, and the mean orbital velocity is 18 miles a second, or about 66,000 miles an hour. The Earth's path around the Sun is not perfectly circular. We reach perihelion in January and aphelion in early July. The seasons are not caused by the changing distance, but to the tilt of the Earth's axis, which amounts to 23½ degrees to the plane of its orbit around the Sun. The fact that the Earth is 3 million miles closer to the Sun in January makes very little difference, and the effects of our climate are more or less masked by the unequal distribution of land and sea in the two hemispheres. The Earth has a diameter of 7,927 miles as measured through the equator, but only 7,900 miles as measured through the poles. This is because the Earth is noticeably flattened, rather less than that of Mars, but more so than the planets Mercury or Venus. The Pacific gravity is 5.5, so that the Earth weighs 5.5 times as much as an equal volume of water will do. Mercury is of about the same density, Venus and Mars rather less so, while the giant planets are as different in nature that comparisons are pointless.
Nine planets orbit an average-sized star in the Milky Way galaxy, the Sun. The third planet in the solar system is Earth. Our closest neighbors, Venus and Mars, are the most similar to Earth, yet a closer look reveals they are very different worlds. Venus is closest to Earth in size, mass, and gravity, but it has a dense atmosphere of carbon dioxide, and there is almost no water. The surface of Venus is extremely hot, with an average temperature of over 800 degrees Fahrenheit. Mars is about half the size of Earth and has only a thin atmosphere. Its surface is cold, with temperatures falling to minus 190 degrees Fahrenheit. Water is frozen at its poles and possibly under its surface. Our Earth is unique among the planets. Liquid water covers 70% of the surface, and the atmosphere is rich in water vapor. It is a geologically active planet. Yet Earth's most unique characteristic is the presence and diversity of life. Spacecraft and satellites that image Earth have forever changed our view of the planet. We now see Earth's oceans, land, atmosphere, and life as interconnected global systems. The Earth is bathed in energy from the Sun. The oceans, land, and atmosphere absorb and are heated by this energy. The heat absorbed by the oceans and transported by its currents is constantly released into the atmosphere. Heat and moisture from the oceans drive atmospheric circulation and weather patterns. Moisture in the atmosphere forms clouds, which cover an average of 40% of the Earth at any given time. The patterns in cloud motion in this time-lapse sequence show how Earth's winds move in bands or zones, which define regional wind directions. The movement of moisture or water vapor in the atmosphere is important in determining the weather. In the swirling motion of atmospheric water vapor, the hurricanes of 1995 can be seen. The hurricanes form off the coast of Africa and move west across the Atlantic to the Caribbean and the east coast of the United States. Our global climate is also influenced by the way heat is distributed in Earth's oceans. Changes in sea surface temperature are shown here. The warmest surface water is indicated in red and the coldest in blue. With such data, it is possible to detect the anomalous increase in temperature that occurs when the normally cool water of the Eastern Pacific is replaced by warmer water. This phenomenon is known as an El Niño. An El Niño can disrupt climate on a global scale, causing widespread droughts and floods. Draining the oceans reveals that the Earth's solid surface, its crust, is divided into highlands and lowlands. The highlands are the land masses that form the continents, and the lowlands form the ocean basins. The Earth's crust is not a fixed, continuous shell. It is broken into a mosaic of moving plates. As these plates move and shift against one another, they release enormous amounts of energy in the form of earthquakes. The yellow dots show the locations of earthquakes that occurred from 1980 to 1995 with magnitudes greater than 4.5 on the Richter scale. These earthquakes clearly mark the boundaries of the Earth's plates. As oceanic plates are driven under continental plates into Earth's mantle, they begin to melt. The molten rock rises to the surface, forming volcanoes. The red triangles show the locations of recorded volcanic eruptions that occurred from 1960 to 1995. Like earthquakes, most volcanoes are located near plate boundaries. The oceans, atmosphere, and land all play critical roles in sustaining life on Earth. The characteristics of ocean currents, wind patterns, and topography can make one area a desert and another a rainforest. Seasonal changes greatly affect Earth's plant life or vegetation. The shades of green and yellow show how leaf-bearing plants green up and decline through the seasons of the year. The vast deserts of North Africa, the Arabian Peninsula, and Central Asia are easily recognized because of the lack of vegetation. The influence humans have had on the Earth can also be seen from space. Viewing the Earth at night, we see the light of countless villages, towns, and cities pour into space. Major population centers, shown in white, are prominent sources of light. Fires from slash and burn farming and burn-off of natural gas in oil fields are shown in red and yellow. From this perspective, the scale of human activity on the Earth can be appreciated. It spans the globe. Global monitoring of the Earth is helping us to understand the complex interactions between the atmosphere, oceans, and land, and their impact on life. Only through a global view can we truly appreciate our Earth as a planet.
Geology can tell us a great deal about the evolution of the Earth. It is the very beginning of a story which remains somewhat obscure. Probably the Earth lost its entire original atmosphere, and after a while a new atmosphere was produced by gases sent out from below the crust. There must have been intense volcanic activity on a scale that we find difficult to visualize. At first, the atmosphere was composed largely of water vapor and carbon dioxide, but then the bulk of the water vapor condensed out, leading to the formation of the oceans. With the spread of plant life onto the continents, the health situation changed, since the first plants and microorganisms extracted much of the carbon dioxide from the atmosphere and replaced it with oxygen. If we could go back to, say, the Cambrian period 500 million years ago, we would find ourselves unable to breathe. Land plants had not appeared, so that there would be too much carbon dioxide in the atmosphere. The rigid outer crust and the upper mantle of the Earth's globe make up what is termed the lithosphere. Below this comes the asthenosphere, where rock is partially melted. The crust has an average depth of 6 miles below the oceans, but down to around 30 miles below the continents. The base of the crust is marked by the Moho-Rosovičić discontinuity, or the Moho, named after the Yugoslav scientist Andreja Moho-Rosović, who discovered that the velocity of seismic waves changes quickly at this depth, indicating a sudden change in density. Between 30 and 60 miles below the surface, the lithospheric rocks become hot and structurally weak. The Earth's crust is divided into 8 major plates or highlands and over 20 minor ones. The boundaries between the continental plates are associated with transform faults, spreading, subduction zones, earthquakes, volcanoes and mountain ranges. The continents drift around relative to each other. This was first proposed in 1915 by the Austrian meteorologist Alfred Wegener, which had led to the science of what is called plate tectonics. Below the lithosphere comes the mantle, which extends down to 1,790 miles and contains 67% of the Earth's mass. Partial melting of the mantle material produces basalts, which flow from volcanic vents on the ocean floor. The base of the mantle is marked by the Gutenberg discontinuity, where the rock composition changes from silicate to metallic and its state from solid to liquid. A reservoir of water 3 times the volume of all the oceans on the surface of our planet has been discovered deep beneath the Earth's surface. The water is hidden inside a blue rock called Rigvodite that lies 440 miles underground in the mantle, a layer of rock between the Earth's surface and its core. The size of the reservoir throws new light on the origin of Earth's water. Some geologists think that water arrived in comets as they struck the planet, but the new discovery supports an alternative idea that the oceans gradually oozed out of the interior of the Earth. However, it may well be that life on Earth originated from comets, because evidence from visiting spacecraft has shown that they are rich in DNA-forming chemicals. A team of geologists led by Stephen Jacobson of Northwestern University in Evanston, Illinois, used 2,000 seismometers to study the seismic waves generated by more than 500 earthquakes. These waves move through the Earth's interior, including the core, and can be detected at the surface. They make the Earth ring like a bell. By measuring the speed of the waves at different depths, the team could figure out which types of rocks the waves were passing through. The water layer revealed itself because the waves slowed down, as it takes them longer to get through soggy rock than dry rock. Water is made up of H2O. Scientists have found that the water inside the Earth has a different composition of hydrogen than that we expect to find in Earth's oceans, as Dr. Lydia Harris from the University of Glasgow explains.
The way that we determine where water came from for each planetary body, it's to do with the different types of hydrogen that are in the water. And what we found is that the composition of hydrogen in the deep mantle of the Earth is actually different to the composition of hydrogen that we find in the oceans on the surface of the Earth. So what we can tell by that is we look at different bodies in the solar system, such as comets and asteroids, and they all have distinctive hydrogen compositions. We can look at the deep Earth and say, okay, well, this means that the composition of hydrogen down there didn't come from comets. It's more likely to have come from very early in the solar system, before planetary bodies formed, the very beginning, what we call the protosolar disk. The composition of hydrogen back then was similar to the composition that we see in the deep mantle today, which means that the hydrogen at the surface of the Earth has been processed in some way. Most likely the processing being that because we have such a thick atmosphere, Earth is continually losing hydrogen to space, and that's changed the composition of the surface water, but it hasn't touched the deep mantle's water because the deep mantle is protected. It's not affected by surface processes.
The outer core extends down to 3,140 miles and contains 30% of the Earth's mass. The inner core, down to the centre of the globe, is solid and has 1.7% of the total mass. It has been said to float in the surrounding liquid core. The core is iron-rich. The solid inner core, approximately 15,000 miles in diameter, is thought to have a central temperature of about 4,500 degrees centigrade, with a density of 13 grams a cubic centimetre. Currents in the liquid core are responsible for the Earth's magnetic field. The outer boundary of the solid core is known as the Lehmann discontinuity, first identified by the Danish scientist Inge Lehmann in 1936. Now, what about the tides? The Earth is accompanied in space by the Moon, and in terms of size, it is about 2.5 times smaller than our world, so most astronomers consider the Earth-Moon system as a double planet. The Moon orbits around the Earth. When we look up on a clear evening, we can see the Moon's changing phases each passing day as sunlight lights up the lunar surface. The Moon's phases changes from new moon, first quarter, full, last quarter, and back to new once again every 29 days, which is the time it takes to orbit around the Earth. The Moon is important to life on Earth because it steadies the slow wobble of the Earth's polar axis, it regulates the length of the Earth's day, and causes the tides in the oceans. About 4 billion years ago, the Earth's day was only about 21 hours long, as compared to 23 hours, 56 minutes today. And as the Moon slowly moves away from us, our day will slowly get longer. The effects of tidal friction increases the Earth's axial rotation period by an average of 1.7 meters every century. The Earth's tides happen because the Moon's pull tends to heap up the waters of the oceans and to keep a bulge of water below it. As the Earth spins, the two tidal bulges, one below the Moon and the other on the far side of the Earth, sweep right around the globe, so that each point has two tides every day. The Sun also causes tides, but solar tides are weaker than lunar because the Sun is so much further away from us. When the Sun and Moon are pulling together in the same direction, or in exactly opposite directions, we have strong or spring tides. This occurs at full moon and new moon. When the Sun and Moon are pulling at right angles to each other, we have the weaker neap tides at either first quarter or last quarter. Our Earth has been studied intensely by scientists since the dawn of the space age, and today we know a great deal more about our planet and the vast diversity of life here, which is helping space scientists unravel the mysteries of the asteroids and the moons of our solar system. In February 2016, the third Sentinel satellite for the Copernicus program was launched into Earth orbit by the European Space Agency, which will study the Earth in great detail.
Copernicus is the most ambitious Earth observation program to date.
It is not sufficient to monitor the evolution of the ice cap or to monitor the sea level rise during 5 years and then stop. We really need to monitor those things over a very long time period.
Headed by the European Commission in partnership with the European Space Agency, Copernicus gathers Earth data from space, air and ground stations and channels it into a wide range of support services. At its heart is the Sentinel family of satellites.
Each Sentinel has a specific duty. Sentinel-1 is more specifically tailored to emergency response. Sentinel-2 is focused on monitoring of the land. Sentinel-3, together with Sentinel-6, is focused on the monitoring of the ocean and waters. Sentinel-4, together with Sentinel-5, is specially tailored to the monitoring of the atmosphere.
There are 2 satellites for each Sentinel mission, A and B, flying in the same orbit. Sentinel-1's highly developed radar instruments see through clouds and rain during day and night. Applications from Sentinel-1 include identifying minute changes in volcanic activity or potential flooding.
So what you can see here on the screen is the first ever Sentinel-1 derived flood map. It was actually used by the Department of Water Affairs of Namibia for the monthly flood reporting, and most importantly, this kind of data is used to plan mitigation measures.
Sentinel-2, with its single multispectral instrument, provides a new perspective on land and vegetation.
It will allow us to monitor the Earth in different spectral bands every 5 days, continuously and systematically.
Data from Sentinel-2 serves agriculture, forestry, disaster control and humanitarian relief. Sentinel-3 will provide thorough and detailed mapping of the oceans. The oceans play a crucial role in the Earth's heating and cooling system.
Ocean temperatures have been increasing, but not so much in the last couple of years. And one of the possibilities is that more heat has gone deeper into the ocean.
The oceans also contain more life than anywhere else, including plankton, which have a vital role in regulating the Earth's atmosphere and climate.
You can think of them as the ocean analogue of the canary in the coal mine. They will respond very, very rapidly to any change.
Sentinel-4 will monitor the atmosphere from a geostationary orbit, while Sentinel-5 will monitor the atmosphere from a polar orbit. Sentinel-6 will use a radar altimeter to measure global sea surface level. All the data collected by Copernicus and the Sentinel satellites is provided free of charge to encourage maximum use. Policymakers, for example, require high-quality scientific data. A subtle shift may be of vital importance.
Very often it's just one number or a few numbers, but these numbers help decision makers to better understand how Europe is changing, how our planet is actually changing.
And we believe also that this Made in Europe data is also an article on which we can build a lot of business development.
Copernicus and the Sentinels can fill crucial gaps in current services.
About 90% of the worldwide good traffic goes by ship. And we don't have, at present, a global monitoring system to monitor ship traffic.
Just for the Copernicus, we have 14 satellites at the moment under development, covering all aspects of environmental monitoring, from ice to land to ocean to atmosphere.
Copernicus is the most ambitious Earth observation program to date. It will provide accurate, timely and easily accessible information to improve the management of the environment and to allow us to understand the effects of climate change. The Earth's atmosphere is made up of several layers. The lowest is the troposphere in which we live. It extends up for about 5 miles at the poles and 11 miles at the equator. It contains over 3/4 of a total atmospheric mass of 5 billion tons. Half of the total mass of the atmosphere lies below an altitude of 3 miles, while 80% of the total mass is contained in the troposphere. Above the troposphere comes the stratosphere, ranging between 7 and 30 miles. The temperature here is constant at about 20 degrees centigrade, and there are high velocity winds, although in these rarefied regions even a howling gale has little force. Ozone is a type of oxygen. The ozone layer lies in the stratosphere at an altitude of between 9 and 22 miles. It absorbs 97% of the sun's ultraviolet light, which would otherwise be very dangerous to life on Earth. Continuing upward, we come to the ionosphere, from 40 to 400 miles. It is here that we find the layers which reflect some radio waves back to the ground, making long-range wireless communications possible. The mesosphere ranges from 30 miles to about 50 miles. Above this, we come to the region often called the thermosphere, up to about 430 miles. It is within the range of the International Space Station and artificial satellites. British astronaut Tim Peake spent 6 months on board the International Space Station carrying out experiments and conducting a spacewalk. Before Tim returned to Earth on the 18th of June, he sent this message from space.
We always talk about seeing the view of planet Earth and how beautiful it is, and being able to go to the cupola and look at that amazing view of planet Earth. But what people don't mention that much is just when you look the opposite direction and you see how dark space is. I mean, it's the blackest black, and you realize just how small the Earth is in that blackness, and that was a real surprise to me. The feeling of zero gravity is a bit like the first time I put on a pair of skis and tried to go skiing. It does take a while to become proficient, and it also takes a while to get orientated, but it's amazing how quickly your brain really adapts to that. I've been amazed at how quickly the body has adapted. You do feel disorientated and dizzy, but on my second morning I woke up feeling fresh, ready to go to work, and have had no problems since. The view of planet Earth is just spectacular. Day, night, auroras, thunderstorms, it's just incredible. We spend almost every free moment that we have looking out the window and taking photographs. We're kept very busy during the day, of course, but in the evenings we get some free time. But our daily routine is really working from about 7 in the morning till 7 at night, and it's mainly scientific activities here on board the space station. There are a couple of things that have really struck me. First is just how thin our atmosphere is, and I kind of knew that from seeing photographs of other astronauts, but to actually see it yourself, and especially at sunrise and at sunset. And of course we orbit the Earth 16 times a day, so we get plenty of sunrises and sunsets, and you can see that tiny, tiny band of which our atmosphere is contained in and how fragile our atmosphere is. That was really quite incredible to see with my own eyes. I was very fortunate to do a spacewalk about 3 weeks ago with my crewmate Tim Kopra from NASA, and we had to go and repair an electrical component right at the very edge of the space station, the furthest part of the space station, and that was absolutely incredible. We had to repair it during the eclipse because the power from the sun, obviously coming through the solar panels, we had to make sure we were in the shadow before we could repair that component, and we got an opportunity to wait for the sun to go down and to take some photographs and enjoy the view of planet Earth. I was just very happy, very comfortable outside, and it felt quite peaceful. It felt quite calm working out there. It was really the most incredible experience of my life, being outside the space station in a spacesuit. We will be doing about 250 experiments during this 6-month stay in space. To give you an example, a couple of weeks ago, Tim Kopra, my NASA counterpart, and myself, we were in the airlock, and we were using the airlock as a hyperbaric chamber, taking it to a reduced pressure so that we could investigate the lungs and nitric oxide as an indicator of airway inflammation. And this is going to have benefit for people who suffer from asthma, for example, on Earth. Last week we were looking at combustion techniques and actually lighting fires on board the space station, which sounds a bit remarkable, but all in a very controlled environment. But the serious side of that is to try and find better combustion techniques for back on Earth, again for cleaner engines and more efficient engine systems. All of these research experiments we do have knock-on impacts and benefits for people back on Earth, as well as helping us to progress further in our exploration of the solar system. I've been trying to share this mission as much as possible with everybody back on Earth. I think it's our responsibility as astronauts to do that. I just wish that I could bring everybody up on board here to look at planet Earth and to see it through our eyes. It's just the most beautiful place I can imagine, and it really brings it home how we need to look after each other and how we need to look after our planet.
The ionosphere is a part of the atmosphere ionized by solar radiation and extends from 30 to 620 miles above the Earth. It is rather like a teardrop in shape, with the tail pointing away from the sun. On the sunward side of the Earth, it extends for only 40,000 miles, but on the dark side, it reaches out much further. The sun sends out streams of particles making up what we call solar wind. When these particles come towards the Earth, they meet the magnetic field and produce a shock wave. Inside the magnetosphere is the plasmasphere, a donut-shaped region containing low-energy charged particles, or plasma. This region begins at a height of 37 miles and extends up to over 30,000 miles, which includes the ionosphere. This region rotates with the Earth. Inside the magnetosphere, there are 3 zones of intense radiation, known as the Van Allen zones, in honor of James Van Allen, the American scientist who was mainly responsible for their discovery. The first 2 zones were detected with instruments carried on board Explorer 1, the first successful US satellite, which went up on February the 1st, 1958. The 3rd zone was detected very recently and is caused by a tidal wave of charged particles from the Sun. There are 2 main belts, one with its greatest intensity at 3,000 miles and the other at 10,000 miles. The inner is made up chiefly of protons, while the outer consists mainly of electrons. The Earth has a fairly strong magnetic field. At the equator, it amounts to 0.3 Gauss. It is essentially a magnetic dipole, so that its shape is rather like that of a bar magnet, and there are two well-defined poles. The magnetic poles are not synchronized with the Earth's poles of rotation, so that a compass does not point due north. The magnetic poles are not fixed in position. The north magnetic pole is drifting in a northwesterly direction at a rate of about 25 miles a year. The south magnetic pole is drifting more slowly at 3 miles a year. When the Sun is active, very energetic particles sent out from it, which arrive in the Vallenberg region. What follows is not entirely clear, but it involves a process called magnetic reconnection. The Van Allen zones become overloaded and particles cascade down into the ionosphere, causing the lovely glows of the aurora.
ESO's La Silla Observatory on a moonless night, deep in the Atacama Desert of Chile. It should be very dark, but strange green and red colors can be seen to shimmer in the sky. What are these mysterious glows? And why do they seem to be getting more frequent? The Sun is constantly showering the Earth's atmosphere with radiation at many different wavelengths. Solar ultraviolet light destroys oxygen and nitrogen molecules during the daytime, and this triggers a chain of complex chemical reactions. As a result, new molecules like ozone are created. When night falls, some of these molecules take part in further reactions and collisions, causing them to radiate light. This process is known as chemiluminescence. The result is seen in the night sky as an eerie glimmer, an effect called airglow. To the naked eye, the colors of this airglow are invisible, but sensitive wide-angle photographs show the fine green or reddish tinges of this phenomenon. Sometimes, airglow appears to be just a faint tinge of color on the horizon, but it can also be a menagerie of changing colorful shapes. The green layer of airglow lies about 100 kilometers above the ground. Here, it is seen from the International Space Station. But there is also a much fainter, reddish tint of luminescent air at altitudes of 150 to 300 kilometers. The extent, color and brightness of the airglow vary with time and place, and are influenced by many different factors. For example, the red glow tends to be brightest at the start of the night, and around midnight and later it can be very weak. And Cerro Paranal, home of the VLT, happens to be located below what is known as the South Atlantic Anomaly. Here, the Earth's protective magnetic field, which prevents particles from reaching the surface, is reduced, and more particles from the Sun hit the atmosphere. This can lead to brighter airglow. Airglow can also appear in strange formations called gravity waves. They are formed by alternating air pressure layers that can grow with height as the air thins. We understand what causes airglow, but why are we seeing more and more of it in photos taken at ESO sites in Chile over the past 5 years? Has airglow become more common? Could it be caused by some global change in weather patterns? The answer is not clear. The recent rapid development of digital cameras seems to play a role, allowing fainter details to be picked up in the night sky more often. But identical cameras have revealed dramatically different skies just weeks apart. Since airglow is triggered by ultraviolet radiation emitted from the sun, changes in solar activity can have a big impact on the brightness of the airglow. The sun cycles through periods of low and high activity every 11 years, and was active in recent years. This, it seems, is the main reason for the recent increase in airglow. The most recent cycle of high solar activity, coinciding with more sensitive digital photography, has provided our first detailed look at this strange phenomenon. Airglow can be beautiful and photogenic, but it also affects scientific observations. Certain kinds of airglow give rise to background patterns in near-infrared images from the VISTA telescope as the airglow structures move in between exposures. One way or another, it's a feature of the celestial display over the ESO sites. Even in one of the darkest places on the planet, the sky is never completely dark.
In this program, I've only been able to give a short guide to our home planet. Scientists are today very busy studying many different topics relating to the Earth, its life forms, climate, weather and geophysics. Hopefully, you have now learned enough to see how our Earth fits into the solar system as a whole, and we are learning new things all the time. That is all we have time for this month. Thank you for watching. Please visit our website, Astronomy in Space Blogspot, where you can see all of our past shows. All of our programs are free to watch, so please subscribe to us on Vimeo or our website so that you never miss a show. Until we come back next month, good evening.